Okay, so we have the components or the parts of the atom. And so the composition of the atom is going to be electrons, protons, and neutrons. And then we're going to see how they're arranged structurally. And so originally it was hypothesized that the particles were uniformly distributed. And that's a plum pudding model. The electrons were like the plums in pudding, or raisins in pudding. And so the negatively charged particles, electrons, embedded within a positively charged spherical gel. And so everything was kind of uniformly distributed, and that's a pretty good hypothesis. But what happened was this: observation pretty much meant that the hypothesis was wrong. And so basically, this experiment determined that the atom consists of this type of structure, which there's something called the nucleus right in the center. And then outside the nucleus is mostly empty space. We'll talk about that. This is the Rutherford scattering experiment, or the Rutherford gold foil experiment. Rutherford took a piece of gold foil and then shot, not a beam of electrons. This like cathode ray tube would be like a beam of electrons that you could shoot. But what he shot was these things called alpha particles. Alpha particles form through the decomposition of radioactive atoms. So you have radioactive atoms in here, and a chunk of the radioactive atom breaks off. There are a lot of them here, and so we develop a lot of chunks, and these chunks are all alpha particles. And so alpha particles are small pieces of atoms that shoot out here. These small chunks consist of like 2 protons and 2 neutrons, which we'll talk about in a little bit. Most of these alpha particles, which are very small, went straight through. And so those are called undeflected alpha particles. So the alpha particles just shot through. They shoot through the gold foil as if there's nothing there. And pretty much there is nothing there, because most of the atom consists of empty space according to the nuclear atom model. However, some of these are deflected at light angles, but others are completely deflected at high angles here. And so if an alpha particle comes close to the nucleus, there's going to be some repulsion, because alpha particles consist of protons and neutrons. Protons are positively charged. Now, that means the nucleus here must be positive or negative. If they're being deflected away from the nucleus, is the nucleus positive or negative? The alpha particles are positive. The nuclei must be positive. And so these are positive. So positive is going to cause repulsion and deflection. However, if an alpha particle goes straight into the nucleus, then it's like trying to push together 2 positive particles. 2 positive particles are going to reject each other. It's like magnets. And so they set up strong repulsions in which the neutron is completely rejected or deflected back. And so this kind of scattering pattern led to this new model. It wasn't that somebody proposed this or hypothesized this, it just came from observation. Now, a plum pudding, if the atoms consist of plum puddings, then most of them will go through, some of them will be deflected, based on where the raisins or the negative charged particles are. But you wouldn't expect high angles of deflection like this in the plum pudding model. And so first came the observation, and then came this hypothesis. Hypothesis of the nuclear atom model. If we look at the nuclear atom in more detail, then these are its major features here. Every atom contains a small and extremely dense nucleus. The reason is because the nucleus contains all the positive charge. In other words, all the protons must reside in the nucleus. The protons are heavy. And it turns out also the neutrons lie in the nucleus as well. So if the protons and neutrons lie in the nucleus, and electrons are 2,000 times lighter, then the protons and neutrons are going to consist of most of the charge of the atom. And therefore, these are small and extremely dense. Well, how dense? It's got to be extremely dense. If you think about the gold, the density of gold is up there. It's about what? Density of gold. 20 times that of water. Water is 1, so gold would be about 20 grams per milliliter. And so that's about as dense as you're going to get. Gold, iridium, platinum, those are highly dense, but they're all around this around 20, let's say. Do you know what the density of the nucleus would be? Oh, it's got to be a lot more. So we'll take a look at that in a second. The major volume of the atom, in other words, practically all of the atom consists of empty space. The alpha particles just went straight through. So there's got to be a lot of empty space. And so the space outside the nucleus is thinly populated by electrons. So electrons occupy that empty space around the nucleus. The total charge of the electrons balances the total charge of the protons. That is, we have electrical neutrality. Let's just, going back to those same points. So most of the atom is empty space occupied by the electrons. Electrons don't weigh much. And then you have this tiny nucleus in the center. The tiny nucleus is going to contain the protons and the neutrons. And so that tiny nucleus contains nearly all the mass of the atom itself. This outside the nucleus doesn't weigh much. It's just the electrons occupied there. And so all the positive charge here, all the negative charge out here. Okay, the positive and the negative charge is equal in a neutral atom. So how big are atoms? Atoms are very small. About how big are they? About, well, what is 10 to the minus 10 meters? A picometer is 10 to the minus 12. So if this is 1 times 10 to the minus 10, we can convert that. 1 times 10 to the minus 10 meters is equivalent to how many times 10 to the minus 12? So if we make this smaller, we're going from minus 10 to minus 12, so this goes smaller. This has to go bigger. So this is 100 times 10 to the minus 12 meters, which is 100 picometers. So an atom is about 100 picometers in diameter. We could also use nanometers, but if we use nanometers, which is 10 to the minus 9, if we go bigger here, so we're going from 10 to the minus 10 to 10 to the minus 9, we have to go smaller here, so 0.1 times 10 to the minus 9. And so what we could say is that atoms are 0.1 nanometers in diameter, or 1 times 10 to the minus 10 meters, or 100 picometers. Which one's most convenient unit to use for the diameter of an atom, you say, out of those three? Picometers. Well, to make it easier to use meters, somebody defined this. You know what times 10 to the minus 10 meters is called? It's called an angstrom. And so we have two choices. We could say 0.1 nanometers, 1 angstrom, or 100 picometers. They all mean the same thing. Which one's most convenient? Still picometers is most convenient, even if we do this. The reason is let's say the diameter is 154 picometers. If it's 154 picometers, that would be 1.54 angstroms. Well, 1.54, you have to say that point, so it makes it a little less convenient. It's nicer if there's no decimal point, so we could just say 154 rather than 1.54. And so this is why picometers is preferred. You don't have to include a decimal point. Place in there. Well, that's an atom, but how big is a nucleus? The nucleus is tiny. And if we look at this, a nucleus is 10 to the minus 14 meters. So if an atom is about 100 picometers, then the nucleus is 1 times 10 to the minus 14 meters, which is how many picometers? Well, if we make this smaller, so we're going from 10 to the minus 14 to 10 to the minus 12. Then we make this, actually, we're not making this smaller. We're making this bigger. Minus 14 to minus 12, therefore we make this smaller by 2. So it's 0.01 times 10 to the minus 12 picometers. And so the nucleus is 0.01 times 10 to the minus 12 picometers inside. And so when we look at this, we're going from 100 to 0.01. Do you know that's 10,000 times. And so the atom's 10,000 times bigger than the nucleus, or the nucleus is 10,000 times smaller than the atom. So 1 to 10,000. And so the usual way to visualize this is like a football field. If you look at a football field is 100 yards. And so if an atom were a football field in diameter, how big would the nucleus be? Like 1 yard? 1 foot? How big would the nucleus be? If the atom were 1 football field in diameter, then the nucleus would be, you say 1 foot? 6 inches? Half a foot? An inch? Half an inch? Half an inch? Yeah? Yeah, so if the just do a rough calculation. So a rough calculation is this: 100 yards is about how many meters? This is a rough calculation. 100 yards is about how many meters? 100 meters. And so we're dealing with 100 meters. What's 10,000 times smaller than the meter? In other words, how many centimeters are there in a meter? There are 10,000 centimeters in a meter. Which means to get this 1 to 10,000 ratio, the nucleus would be 1 centimeter. 1 centimeter is less than half an inch. And so if the atom were a football field, then the nucleus would be like less than a half inch in size. And that contains all. So if you have a gold atoms are heavy, right? Gold atoms are heavy. Gold is dense. But gold atoms consist of lots of matter packed in that atom, or lots of empty space. Lots of empty space. So even though a gold atom is very dense, it's one of the densest things that you know, it's mostly empty space. That gold foil, what was it? Mostly empty space. And what's the density of gold? About 20 grams per milliliter. Now if we do the calculation, and we calculate what's the density of the gold nucleus. Do you know what the density of the gold nucleus is? If a gold atom is mostly empty space, then the gold nucleus has to carry most of the mass, or most of the density. And so the density of a nucleus is not like 20 grams. The density of the nucleus is like 200, not 200, 2,000. The density of the nucleus is 2,000 tons. 2,000 tons per milliliter. Can you imagine 1 milliliter having 2,000 tons of matter? It's mind-boggling. So the density is the density of the nucleus is incredibly big. So how was this model discovered? Just to reiterate, it's discovered by the experiment. What was the experiment that confirmed or led to the hypothesis of the nuclear atom model? Rutherford's gold foil experiment, in which the alpha particles, most alpha particles were not deflected. Some were deflected at high angle due to the positive propulsion. That's the high angle repel backwards there. Some were lightly deflected. Depends on how close they got to the nucleus. So that pretty much confirmed it. We talked about the proton and the neutron already. Talked about the electron. Now let's talk about the number. And so we kind of have an idea of how things are structured. You know, there's going to be a nucleus. Now we just got to figure out the number of particles. And so let's talk about the number of particles next. Subatomic particles. That an atom has. And so the first thing is Z. Z is what we call the atomic number. it's the number of protons in an atom. It's also called the element number. Because this is the number found in the periodic table. Found in the periodic table. So it doesn't matter. I'll come back to this slide in just a second. But it doesn't matter if the oxygen atom is heavier or lighter. They all have the same number of protons. And so how many protons does oxygen have? Well, it's this number here, 8. Oxygen's element number 8. Therefore, Z is equal to 8, therefore it has 8 protons. And so all oxygen atoms have 8 protons. All right. However, all oxygen atoms don't necessarily weigh the same. They could weigh differently, and they could weigh differently because of something called isotopes. Isotopes are atoms that only differ in the number of neutrons. Number of neutrons, here they capitalize it, which is okay. And so it turns out that all oxygens have the same number of protons, but they might have different number of neutrons. That's going to impact their mass, but it won't impact their chemical properties. So this morning, you probably drank some oxygen, what we call oxygen 16, oxygen 17, and oxygen 18. And so all the oxygen atoms that you consume today have 8 protons. But the difference is in the number of neutrons, and we'll use for neutrons. Oxygen 16 has 8 neutrons. Oxygen 17 has 9 neutrons. Oxygen 18 has 10 neutrons. And so just because it has an extra 1 or 2 neutrons doesn't impact it chemically. The chemical properties are the same. Same chemical properties, same taste. However, their densities are different, and therefore their physical properties are different. So same chemical properties, different physical. Like mass. Now having that extra 1 or 2 neutrons is going to make it heavier. And so when we're looking at the composition, we have another number that helps us understand that. And that's where these numbers come from, the 16, 17, and 18. Those are called mass numbers. So N is neutron, A is mass number. And the mass number is just Z plus N. Z plus N. And so 8 and 8 is 16, 8 and 9 is 17, 8 and 10 is 18. Okay, and that's what we put up here. This 16 is the number we put here to recognize that oxygen has 8 protons, 8 neutrons. This oxygen has 8 protons and 9 neutrons. This oxygen has 8 protons and 10 neutrons. And so the compositions given by this number here, we can tell how many protons by looking at the periodic table. It's element number 8. We can tell how many neutrons it has based on the A, when you add up the Z and N. We get that. These are called isotopes here. And these 3 are what we call naturally occurring. Naturally occurring means in every sample of oxygen, we see 3 different weights of oxygen atoms, but chemically they're identical. Physically they're not identical. You can separate it out. You can separate out the heavier water molecules from the lighter molecules using some kind of centrifuge or some other techniques. want to separate. Not everything has isotopes. When we look at the periodic table, is there any way you can tell? Oops. When we look at the periodic table, is there any way you can tell that there are 3 different oxygens? No. There's no way you can tell. Necessarily. How many different fluorine atoms are there? You know, oxygen and fluorine are right next to each other. So you might try to look for patterns. Like, for example, 3, maybe fluorine has 4, or maybe fluorine has 2. It would be nice if there's some simple pattern that we could memorize, that we could use to predict how many isotopes there are. But do you know how many isotopes fluorine has? 1. There's only 1. And all fluorine atoms in nature, so if you use fluoride toothpaste this morning, all the fluorine atoms in fluoride toothpaste were exactly the same. That is, all the fluorine atoms had, you know how many protons fluorine has? 9 protons. And how many neutrons fluorine has? 10 neutrons. So all the fluorine atoms, except the difference in that is this. This will be an aside. Normally when we're thinking about oxygen and water, those are neutral atoms. And neutral atoms, we look at the total positive charge. The total positive charge is based on the number of protons. There's 8 protons, so the total positive charge is plus 8. And then we look at the total negative charge. But what is the total negative charge? And that's going to come from the electrons. It turns out the number of protons and the number of electrons is the same. It's called electrical neutrality. So there are 8 electrons here. Over here, there are 8 electrons. And over here, there are 8 electrons. In other words, the number of electrons is equal to Z for what we call neutral atoms. Neutral atoms. And so in fluorine, how many electrons would there be? 9 electrons. But then we have the element fluorine. Fluorine consists of 9 protons, 9 electrons, and 10 neutrons. If you brush your teeth with fluoride today, fluoride is different than fluorine. Fluoride is going to have a net negative charge, which we show as a little negative sign here. And that has 9 protons, 10 neutrons, and 10 electrons rather than. So there's an imbalance. We have an extra electron, which leads to this negative charge resulting here. So it's not completely balanced. And we call this fluoride. But we'll talk about this later. This is an aside. And this is called fluorine. And so these are called isotopes. One thing that's very commonly mistaken with isotopes is they're isotopes. Isotopes are the same element but different number of neutrons. These are called ions. Ions have mismatch in the electron to proton ratio. And so those are ions. These are isotopes. We'll talk about ions later on. We're just talking about isotopes right now. And so this is isotopes here, slide 1. Isotopes, 2 or more atoms of the same element that have different masses. What we could say is 2 or more atoms of the same element that have different number of neutrons. And therefore, will have a different mass. So we named the isotopes by age, the mass number. And so this one's named oxygen 16. And so it's just the elemental name times the mass, or all elemental name followed by the mass number, oxygen 16. So here, that's shown here, oxygen 16. There are other ways of representing this. Other ways of representing the composition of the atoms is by a nuclear symbol. The nuclear symbol looks different than a regular chemical symbol. A regular chemical symbol isn't going to have these numbers. In a nuclear symbol, what we do is above we write the number of protons plus the number of neutrons. The number of protons plus the number of neutrons is just the mass number. And down below we write the number of protons. Well, the number of protons is just called the atomic number. And so up here we have A, down here we have Z. Z is often omitted because what element number is carbon? If you look at the periodic table, element number 6 is carbon. And so a lot of people say this is redundant. Can carbon ever not be element number 6? No, because if it were number 7, it would be nitrogen. And so a lot of people leave off Z because the symbol tells us what number it is. We just look it up on the periodic table. And so we don't need that 6. But if you want to be thorough, we'll put the 6 down here. This is called carbon 12. This is called carbon 13. What's the difference? The difference is just one neutron. For example, carbon 12 will have 6 protons and how many neutrons? 6 neutrons. And 6 protons and 6 neutrons will give us a mass number of 12. 6 plus 6. How many electrons do we have? 6. Okay, then we have this other carbon. This is carbon 13. Carbon 13 has 6 protons and 7 neutrons. And mass number of 13, how many electrons? 6, because the number of electrons balances out the number of protons in the neutral atom. Unless we have an ion. If we have an ion, it's different. And so let's go ahead and fill out this table here. So the symbol for barium is, let's go to the periodic table here. Yeah. Symbol for barium is Ba. There. Ba. Barium is a metal. Looks like this. There. Silvery gray with pale yellow tint. So from BA we go to what element number is BA? It's element number 56. So that goes here. The number of protons is 56. The atomic number is 56. Okay, so BA, atomic number 56, number of protons 56. Number of neutrons depends on what isotope we're dealing with. So we have to look. We need to know the mass number. If we know the mass number, then we can calculate the number of neutrons. So if the mass number is 138 and Z is 56, so A plus Z is 138, Z is 56, then the number, actually N plus Z, sorry. The number of neutrons is 82. Mass number is 138. The name of the isotope, this is called barium-138. Barium-138. Let's go back over here. Let's take a look. 56, 56, 82, 138. Barium-138. Let's hope this will fill a line at a time. It doesn't. All right, let's figure out the rest of this. This is oxygen. Elemental symbol. Oh, atomic number. Oxygen is number 8. Number of protons? 8. If we have 10 neutrons, then what's the mass number? 18. And so what's the nuclear symbol? The nuclear symbol is going to be oxygen. You see, this is nuclear symbol there. The only thing I'm missing is the 8 here. But the 8 is not necessary because oxygen is element number 8. So this would be the complete nuclear symbol. And the name of this isotope, we would call this isotope oxygen-16. Oxygen-16 is what most of the oxygen atoms in water comprise. Oh, it's not oxygen-16. What am I doing? It's oxygen-18. 8 and 10. It's oxygen-18. Okay, let's go on to the next one here. Okay, here this one's a little bit more complex. Atomic number Z is 82. So Z is 82. What element is number 82? So we go over here. Element number 82 is Pb, which is lead. Yeah. So LEAD, P, capital P, lowercase b, Pb, lead. How many protons? 82. How many neutrons? Well, it depends on which isotope we're talking about. We can tell what isotope we're talking about by looking at the mass number. It's 206. So we're looking at lead 206. If we're looking at lead 206, how many neutrons do we have? 124. So 124 neutrons. The nuclear symbol is going to look like this. Pb206, 82. And the name of the isotope is lead-206. So let's take a look at that. Lead-206. Let's do the next one. The next one, we're told it's zinc 66. So the name of the element, zinc, Z-I-N-C. The elemental symbol, the symbol for zinc, is Zn, capital Z, lowercase n, Zn. The atomic number, so we've got to look at zinc. What number is zinc? It's Zn. 30. So atomic number is 30. Number of protons? Number of neutrons? Yeah, 36. 30 plus 36 gives us 66. Mass number? 66. Nuclear symbol? Nuclear symbol, I'll just scroll. Would be this. So you have some tables in your homework, you can work on those. That's the composition. So what we're going to do is we're going to try to look for some patterns. Because of course we can figure out the composition of the elements, but what we want to do is we want to figure out the properties. So knowing that something has, let's say, 10 protons, what can you tell me about it chemically? What can you tell me about it physically? Can you tell me anything? Something has 10 protons and 12 neutrons. Okay, tell me its chemical and physical properties. Well, what you can tell me right now is you can tell me that the 10 protons and 12 neutrons are located in the nucleus. The nucleus is a tiny thing in the middle of the atom. And the electrons, which there are going to be 10 electrons, are surrounded in the nucleus in empty space. But what can you tell me about the properties of that? Probably nothing, right? And so what you need to do is this. What we need to do is we need to start memorizing some properties and then trying to look, is there correlation here between the properties and the number of whatever, number of protons, number of electrons, or number of neutrons. And then as we do that, we can try to better understand things. And so here, let's take a look at Dalton's disproof. Atoms can be destroyed and form subatomic particles. Atom smashers are built to do this. And so Dalton said they can. But Dalton, he proposes in the 1700s. All atoms of an element are identical. That's not true because they're isotopes. They're identically chemically, but they're not identically physically. Identical physically. before we get into looking for correlations, the next thing we're going to look at is atomic mass. I asked you, the atomic mass unit. Do they have a 1 AMU mass? AMU or U? Do they have 1 AMU or U mass locked up in some vault? And the answer is no. Do you know how the AMU is defined? There's not a 1U object. You know what there is? There's a 12U object. And the 12U object, they don't have to lock in a vault because it's present all over the place. Anybody can have free access to it. And it was chosen this way because it's easy to obtain. And you don't need any kind of special thing to get it. What weighs exactly 12U is a carbon-12 atom. And so what they decided to do with this one is they decided to call a single carbon-12 atom exactly 12U. And so everybody can get a carbon-12 atom because, carbon atoms make up wood, they make up graphite in a pencil. In fact, graphite is pure carbon. And in fact, graphite is an excellent source of carbon-12 because graphite consists mostly of carbon-12 and a tiny bit of carbon-13. So if you want some carbon-12 atoms, all you do is you get some graphite and you get some carbon-12 atoms off the graphite. And so how do you do that? Well, it's not as hard as you might think. How they do this is this. How do you weigh individual atoms? The way individual atoms are weighed are similar to the cathode ray tube. Remember the cathode ray tube, there's a beam of electrons. And that beam of electrons goes straight unless there's a magnet. If there's a magnet, then they get deflected. Okay, if we had a beam of carbon-12 atoms, how do you generate a beam of carbon-12 atoms? How you generate a beam of carbon-12 atoms is you get a laser, and you get a piece of graphite, and you strike the graphite with a laser. When the laser hits the graphite, atoms are vaporized off the surface. And so we generate atoms that way. And so the atoms are being vaporized off the surface of graphite, and in that mix are carbon-12 atoms. Now the carbon-12 atoms will just continue up. And so what we do is accelerate them. How do you accelerate the carbon-12 atom? You can push it along, or you can suck it, or you can do other things. The way carbon-12 atoms are usually accelerated is you have an electron gun. How do you make an electron gun? You have just what we call electrodes, and you generate a big voltage, and then you generate some electrons, like a little lightning bolt, right? Then you have an electron gun. You strike those atoms. And when you strike them, sometimes electrons stick to the atoms, sometimes electrons knock the other electrons off. And what happens is it makes the atoms charged. If the atoms are charged, then you put a positive plate up here. And so let's say I have a negative carbon atom and a positive plate here. What's going to happen? They're attracted. The negative and positive are attracted. So the atoms get attracted and accelerated. And so these atoms get attracted and accelerated, and then you put a magnet there. And when they hit the magnetic field, they get deflected. Based on the angle of deflection, you can tell how much they weigh. And so let's say you wanted to test your balance. I need exactly 1 kilogram so I can zero my balance. I'm going to put exactly 1 kilogram on there and zero it. What's that called? Calibration. And so I can calibrate it. Well, I have to go to France to get this, but my balances aren't that expensive, so I'll buy a cheap standard. You can buy much cheaper standards. In fact, we have a bunch of standards in a plastic box that's unlocked, that's kept in a drawer inside our laboratory that's not worth that much money. And so we use those. So it's like 10 gram, 100 grams. So we put the 100 gram on there and make sure it's reading 100 grams, right? Just to make sure the balances are reading correctly. Well, we could do the same thing here. So carbon-12 atoms are abundant and cheap. And so what you can do is you can take your instrument. This is called a mass spectrometer, which works like a cathode ray tube. And it's in vacuum. And you can calibrate it that way. So where the carbon-12 atoms hit the screen, the detector, you say, that's exactly 12U. And so there's no 1U standard mass. There's a 12U standard mass accessible to everyone. And so everyone can calibrate their mass spectrometer easily using that if they want. But we can calibrate it with other atoms as well. Once we know where carbon-12 strikes, we can determine the mass of others. It's important that you know how the U is defined because the definition changed. were lasers really prevalent in the 1940s, 1950s? Were lasers very prevalent back then, 1940s, 1950s? So if I want carbon-12, I want to get it in the gaseous phase, like the electrons in the cathode ray, I want it in the gaseous phase. In order to do that, I got to hit it with the laser. But back then, lasers weren't that prevalent. And the other thing, have you ever tried to cook carbon? Have you ever tried to vaporize carbon atoms off graphite? Have you ever tried to melt graphite? No, you're never going to melt graphite. It'll start glowing before it melts. Glowing red hot, white hot. Really hard stuff to melt, hard stuff to vaporize. And so back in the, let's say, pre-1950s, somewhere around the 1950s, they used to use oxygen. The U, how it was defined in the 1950s? The U is defined as the mass of an oxygen-16. What they decided to do is they're going to do, the mass of an oxygen-16 atom weighs exactly 16 U. And so what they decided to do sometime many decades ago is they decided to change the mass. Originally, they said this weighs 1 kilogram, and then they decided, that's not as convenient. This is going to weigh 1 kilogram, and they weigh different amounts. An oxygen does not weigh the same as a carbon. And so all of a sudden, 1 kilogram weighs a different amount. If 1 kilogram all of a sudden weighs a different amount, that means all the old stuff weighs differently than all the new stuff. That means that all the old periodic tables, these black numbers down here are the masses, all of these masses are different than the new periodic table. So if you look at an old periodic table, 1950s, 1940s, something like that, the numbers are all different. The numbers are all different because all of a sudden they decided, I'm going to change what the U weighs to make it more convenient. And so old masses, they change the standard. And so you need to be aware of that. And so you can't use, if you're going to, I just have this really old book and old periodic table, be careful. You don't want to use that because it could give you the wrong mass. So they decided to change it. Okay. Well, anyway, so you need to know the definition. The U is defined as, 1 U is defined as 1/12, exactly 1/12 the mass of a carbon-12 atom. The atomic mass is the average mass of the atoms of an element compared with the atom of carbon-12. The atomic mass is just how many U an atom weighs. That's the atomic mass. We have two different atomic masses, though. We have something called isotopic mass, and we have something called average atomic mass. So, when you think about how many oxygen atoms are in this water, there are so many, you couldn't even count them. So many oxygen atoms. And in here, we're going to have 3 different masses. Some are going to weigh about 16 U, some 17 U, some 18 U. But since you have a gulp of water, do you want to calculate how many of the 16 U oxygens you drank, how many of the 17, how many of the 18? No, not necessarily. What you want to do is you just want to get the average. What was the average mass of it? And so this is called the average atomic mass versus the isotopic mass. If we're interested in the isotopic mass, then we want to know exactly how much each oxygen weighs. And so that comes up with something like neon. The average neon mass, okay, let's look at the average neon mass really quick here. Sorry. We'll just go with copper. Oh no, we're going to go with neons. I have it in my periodic table. All right, there's one more number in the periodic table. when we look at neon, neon has a Z of 10, so there's 10 protons, okay, and 10 electrons, and the number of neutrons depends. Now, I don't know how many isotopes there are. You can't tell by looking at the periodic table. But this number here, this little number, is the average mass of a neon atom. This is the average mass of, and so neon, an average neon weighs 20.180 U. That's it. Okay, that's what's shown in the periodic table. But when we actually weigh out atoms of neon, this is what we're going to see. When we weigh out atoms of neon, we see 3. And so we feed the neon atoms through a machine, which is called the mass spectrometer, and then it hits. You know, the lighter ones are more heavily deflected, the heavier ones are less deflected. And so it looks like most of the neon atoms weigh 20, about 20 U here. And you can see there are a lot more hits here. In fact, the majority of them are 20. There's a small fraction that weighs 21 and a small fraction that weighs 22. And so, since the mass of the proton is about 1 U, the mass of the neutron is about 1 U, then this is neon, what we call neon 20. Neon 20 weighs close to 20, not exactly 20. This is neon 21, this is neon 22. Those are the individual masses. And then we'll take a look at the exact masses there. All right, we're out of time here.